Recording started. Okay, for the benefit of the recording, I have a frequency here, which in my case is 10, your case is probably 15. And then I had Excel compute me the inverse. And then I have dot number, I have my position measurement, and there's my estimate of my error on each measurement. Then to get time, I took dot number and multiplied it by the delta t I calculated, and I used the dollar signs because I always wanted to use that same number. And then once I've got that, I can use my fill handle to go down the line and get all the times. And then here, I grade these guys out because now I'm calculating the difference between two rows. So that means I lose a row. And this is just one x position minus the x position before it. And now no dollar signs because I wanted to pick the next pair each time, and the next pair and the next pair. And we can see that here. Now it's D8 and D7, D9, D8. And then I can, once again, take my fill handle and fill them all in. And so one thing I could do here is that I already don't like the time with all those zeros. So I'll cut down, oops, I like to have two. I always like to have two decimal places. And, I noticed I forgot something. So this is going to be a little tricky. Not super tricky. What happened? Come on. That's weird, huh? Why did she disappear? Well, that's creeping me out. Well, I don't know what to do. Shit. Well, anyways, just to get back to this, I did this data quality, and oh, look at that! It won't go into the spot that's gotten. See, it snapped. It only go. Oh, wow, that's weird. So this also shows you that this is made up data because it's a perfect. It's an x squared fit, and if you recall, you may have learned that x equals 1/2 at squared plus v0x plus x0. So what that's telling me that is when my dot zero, the sled was already moving. So the only thing is, I don't know how to solve this problem. I will try closing and reopening this. Oh, God bless it. Yeah, so this is what you guys did for the pre-lab, and it has the up and the down, but that's physics 2100 and physics 1100. So I apologize for that. All right, what's next? Now, what I forgot was I need a plus minus on delta x. So what I can just do is select this column, and then I right mouse click and pick insert, and yeah, I want to shift all of them right. So now I've got my new column. So I need apostrophe plus minus, and it's delta x. And that's also in seconds. No, it's in centimeters, duh. Okay, so that one we use, there's this error formula. It's not written out well in the lab manual because he uses the symbol, the lowercase delta symbol in the lab manual, but in fact, what we add up, oops, oh, the tablet is, why isn't the tablet working? Okay, so in here, you see the sigma symbol. And the sigma, the circle with the hat on it, like the hair blowing in the wind, that's another word for plus minus. And for us, little a and little b are one. So we just have to add the plus minuses in quadrature. Plus minus one of the, plus minus one squared plus minus the other squared. In our case, that's pretty straightforward. So equals to SQRT, open parentheses, and of this one, and then little up caret, it's called a caret, that's shift 6 squared plus the other plus minus, and they're all equal, so we could dispense with this, but let's assume that we have different plus minuses, so we're going to do it by the book. And enter. Now I'll zoom in on that and highlight it for you. So we're using this error formula. Whoops. And view, zoom to selection. And there it is. So it's the square root of it's x final minus x initial. So we take the square root of x delta, the plus minus x final, and then add it, square it, and then add it to the square of plus minus x initial. And then again, we take our fill handle. And we fill in all of them. And not surprisingly, they're all the same. And then the next one we need is the average t. So we get the center of each window. Oops. And that equals, we can use the average function, average, and then we click on, I think we can get away with it like that. You know, we select those two. Let's see if it works. So this should get us 0.05. Let's see if it works here. Yeah, great. So it's working. I thought we had to like select one time and then do a comma and select the other time, but they are next to each other. Okay, and then we do the fill handle again. And there's our times. So I will highlight that so you can see it. Yeah, why is my tablet not working? It's bugging me. Now, we need to do what our V average is delta X over delta T. And so that's going to equal delta X and divided by, and in this case, my delta T is up here. And we need to add the dollar signs. You can hit F4. Well, maybe not. No, it's not working. Okay, good. I'll just type them in. So when you do it, let's do this again. Equals the box containing delta X divided by the box that has delta T. And now I want to add dollar signs. If I use my arrow keys right now, it'll shift to a different cell. So what I have to do is I have to click inside. And now I can move my arrow keys around. So dollar sign, because I want it to use the same delta T each time. And, so that's 7 centimeters per second already, okay. And then I fill it. And it's going at a pretty good clip there by the end, okay. Let's see, we want to change, let's see what the format is. General, no, we want it to be a number. And there we go. So I will, now you can see that again. Okay, so then we need to get, so is everybody okay? Is somebody left behind and I need to go back to something? Oh yeah, of course you did this already. Did it once anyway, twice almost, yeah, okay, good. Practice makes perfect. So now we have to calculate our plus minus of V average, so we need to go, oh, it did it again. Okay. I'll just restart it. Probably I have to reboot my computer.
All of my V averages are the same.
Okay, so then it must be, are you dividing by delta T? Or are you
Yeah.
dividing by the
By
T
delta.
average? The spreadsheet, reopen it. Okay, so when we calculate, now we have two numbers being divided by each other. And so we have to use the relative error. We've gone over this before. And in this case, we're lucky because we're going to say that the plus minus on T is equal to 0. So we just need, oh, it's not that one, it's this one here on the right. So it's just going to simply be the square root of delta X over X times V average. Okay. So equals SQRT of delta X divided by delta X itself. And in fact, I have to add another parentheses in there. And then square it, and then close it. And then I have to also multiply by the value of V average to get the plus minus. Okay, so that's my plus minus on my V average, which is probably going to be the same for all of them. Yeah, okay, so take number and maybe we'll add an extra zero, an extra place, yeah. Okay, so now we're on our way home. We have the fit, we have the res, we have the res squared, and I'm gonna put the chi-square there. I didn't realize it was in your intro. I was gonna say, I don't like people using trend lines, but I think the trend line will tell us the error on the slope. Okay, so also these guys get blacked out because we're not gonna be calculating them. Anything there? Okay, so we need a fit parameter table. So we have slope, we have y int, we have sum of the res squared, we have sum of the chi squared, and then we have our we'll call it G, acceleration of gravity measured, the acceleration of gravity accepted, and, oh yeah, percent difference. Okay, so that's all the results we need. And we'll make that one a little wider so it all fits. Okay, so let's see if I can guess. So we get 10 times, slope of 10, now that will get me 1.5. Yeah, it looks like a slope of 10 or 12. I'll try 12. And I'll say it's gonna pass through 0. I'm just giving it some seed values just to start. So equals, and then the x component is the t average times the slope, and then we use the dollar signs, and then plus the y-intercept, and we need the dollar signs again. Enter, and then we fill them in, maybe. So there's our fit line. In fact, I see I'm gonna have to format all these things. So I'm gonna just do all of them at once. What I did is I put the cursor up here on the letters and dragged it across. So then this equals data minus fit. Ooh, so that's really off. Maybe, we'll see. Data minus the fit. Enter. Then this equals this squared. And the chi-square, so you saw that already. This is where we divide by the error squared. And what chi-square does is, you may know that sometimes you'll have different size error bars. And does this sound familiar, that you draw a line through the data points the best you can, and also within the error bars? Does that sound familiar at all? No? Okay. What the chi-square does is it takes into account different size error bars, which we don't have, but it allows us to do something else. So we'll just calculate it for now, and we'll see if we use it. So it equals the res squared divided by the plus minus squared. And it's going to be a pretty big number. Yeah. Now I can fill all of them at once. And there they go. Yeah, so it looks like the slope has to be a little bigger. And, oh, bigger still, huh? Okay, but we'll let the graph do that for us. Okay, so this, we sum the res squared equal sum of the res squared and enter, and this equals the sum of the chi-squares. We're almost done, guys. Okay, so now's the time to enter the graph. So we pick our t average and our v average, and we enter in a scatter plot. There it is. Now, this is the time to enter the error bars, because if we add the fit line and we add error bars, it'll add error bars to the fit line too, and then we have to get rid of them. So this is just we get from experience. So we have error bars. I don't know, standard error is good enough for now. Then we double click. I'm going a little fast because we've been through this a few times now. And Mac users have to click Format up here, and this drop-down box, and then X error bars first. Windows users can do that. Windows users can also go up here and pick X error bars. We pick the bar graph icon, fixed value, and we want it to be 0. No X error bars. And then the next thing is to format the Y error bars. And now we use custom value. Oops. Come on. And the custom value is these plus minuses we calculated. And the plus minus, again, the same numbers. It's probably going to be awfully small. We probably can't even hardly see them. And that happens to be true. We can't see them. Wow. That's incredible. They're not even, I wonder if, let's make sure. We can do a double check if they're actually there by making, well, two things. One thing is that we can make the dots of this small, marker, built in, and make them smaller. Yeah, that the error bars are starting to appear. Or I can just do that, so I can make one error bar really big, and there you see it pops up on the graph. Okay, so now we want to add our fit line. Select data, add, series name is fit. You just select the box. X values are T averages. And the Y values are the V averages. And then something should jump on. Yep, there they are. Oh, wait a minute. That's not right. It's the fit values over here. I'm saying they can't possibly be the exact same. They should all be in a straight line. And there they are. Okay, yeah, the fit line's always, even when it's dots, has to be a straight line by definition. So then we want to format that and say we want a solid line. I like to make it a little thinner. We can stick with the orange this time. And marker options, none. Oh, the fit line, of course, the fit line is blue. We don't want blue.
See you, Professor.
All right, see you later. What happened? I thought the fit line was going to be orange. And, well, we'll just make it red as usual. Okay, and so we can now let the solver do our work. Data, solver, and, okay, I know that. Okay, so we're going to minimize. I'm going to pick the chi-square, the sum of the chi-square, because we might use it. And then we want to change the slope and the y-intercept. And, yeah, it looks like all good. And it snapped right onto the data points. So one thing is to check and see if the fit line looks good, because if you say okay at this point, you can't use the back button. So sometimes it gets you really wild values, and so and you want to restore it to what it used to be, but we don't want that. Okay, so that means then that our G measured is equal to the slope times the length divided by the height. And the accepted one is 980. And let's format this. I should have formatted the last one too, duh. Okay, so what percent difference? Oh, I'll zoom in on it. Okay. So it equals absolute value of the two values, so the measured value minus the accepted value, close the parentheses, and, oh, wait a minute, I see. We need to add an extra parentheses. And then, right, then we divide by, shit, easy, Harry, take it easy. We measure the difference divided by the average, right? Divided by the average of the two numbers, and they're next to each other again. Close the parentheses, and we need one more, yep. Oh, and I forgot times 100%. Wow, not bad. Well, this is artificial data, so of course it's going to be good. And what do I? Oh yeah, I want to format it. I'll highlight that again so you can see it. Number, and I just want to. I have to zoom it out slightly. Zoom to. We'll try 200. And yeah, there it is. It's the absolute value of the difference divided by the average of the two times 100, which of course may look familiar anyway. Now, let's see. We may have a quick and dirty way of finding the error. If I normally don't like students using trend lines, but you guys have already had some experience doing curve fitting, so I wouldn't lose my mind if you did a trend line. I'm just wondering, so it gets the same. I wonder if it's going to give the error on its, linear display equation. And so, oh, that's right. It doesn't give the error. Okay, that stinks. But it's not hard to do. So, although I point out there's this R squared test, and if you get a value of 0.9 greater than not 0.9 or greater, that means that your fit is very good. So because you guys are probably in your professional lives going to be allowed to use these trend lines. So how do we get the plus minus on the slope? It's pretty straightforward, and you may have already seen it. So we go back to data, we go back to the solver, and we tell it that we want to, what happened to my fit table? Oh, there it is. I want it to do a value that is the sum of the chi-squared. You see 172.75? We just want it to be 173.75. So that this is true. The plus minus on the slope, oh, I pointed 173, yeah. The plus minus on the slope is the amount of change in the slope that causes a change in the sum of the chi-squared to change by 1. And we only want to vary the slope, not the y-intercept this time. And we solve, and I'm afraid to hit OK. But it got a reasonable number. Okay. So keep it. Now, one more. So now what we do is we take this number, we copy it, we put it here, paste it special, and we only want to paste the value, the number. And then we go back one more time, and we tell it to now minimize it to get the best fit. One more time. And there it is. So now we do, so let's see, this is the slope, this is the extreme tab, and then this is the plus minus on the slope. And it just equals the absolute, oh, I forgot the equal sign, equals ABS of this minus that, and then the percent error is equal to the plus minus divided by the value times 100%. So 0.26. This is artificial data, so don't expect your number to be this good. And, well, I guess I didn't need to do that, but okay. So that means this is equal to this, and it's times, I want to convert this to scale it up. So the L divided by the H, enter. Great. So now Oh, duh. I wonder if this is gonna work. I don't want that one. That's accepted value. Nope. Okay. So I know what to do. I just copy this. Well, let's do it. I'm sorry. I'm getting quite tired, as you might imagine. Imagine you are too. So here we do. This equals the value of G measured times the L divided by H. No, that didn't work. What happened? Oh, duh. Sorry. It's this number. Yeah. Yeesh. One more time. Equals the slope extreme times, boy, I guess I'm already thinking about my alcoholic beverage when I get home, divided by little h, and there it is, finally. So then we get the plus minus of the acceleration, the measured, plus minus g measured equals absolute of this minus that, enter, and then the percent error equals the plus minus divided by the measurement, and then times 100. So yeah, not surprisingly, it's the same thing. So our error bar is smaller than the difference. So that means, in my case, so that means that that my measurement is off. Of course, in the ideal world, the difference between them would be very small, and my 0.26% error on my measurement would look good. So that means that we have some systematic error. That's no big deal. You're not required to get this right. And then while you're here, let's just see what the questions. Plot, is the graph useful to understand what's happening? Well, I think so. It shows us that it's speeding up. The speed accelerating, what is accelerating it? Well, we know that. We did the best fit. Well, these are, I'll have to reword these. So this is all your analysis. For the final logbook, you would print out these tables, make them pretty looking, like I'm putting on the borders. And again, this is final logbook. And then the view, and let's zoom out. So you have the graph, which then needs to be prettied up with labels, and then this table with explanations of what each column means. And yeah, oh, I want to get borders on all this. And borders, there you are. All borders. Okay, and that's it. And then for the conclusion, so that's the result. And the conclusion is, well, did we accomplish it? Yeah, we did pretty good, right? We got a difference of only 0.9%. In my case, you guys, if you get a percent difference that's 10% or less, that's success. And I'll see about those other questions for conclusion. All right, time to stop the recording.